Hello guys, today I'm going to be doing the basic reaction of chemistry, which is the acid-base reaction. Now these are simple reactions, but then they are used in so many situations that it is really a good idea to go over them once in a while. Now before I do that, I'm going to go over the basic terms that we will use when we talk about an acid or a base. So one of the terms is the Bronsted acid. So what is a Bronsted acid? What qualifies as a Bronsted acid? Now, a Bronsted acid is a molecule which is a proton donor. Now, proton can be written as H positive, right? So the hydrogen atom is made of one proton and one electron. And if you take out this electron, right, if you ionize it, you will only be left with one proton. So therefore, you can call H positive as a proton. Now, another term is the Bronsted base. And as you might suspect, it is the opposite of an acid, so it is a proton acceptor. Now here, what is the condition for being a Bronsted acid base? That means the molecule needs to work with a proton, right? For example, if you have water molecule, it has two lone pairs of electrons on it, and we can work with, suppose, phosphoric acid. Now, for sure, phosphoric acid has many protons to donate, but it does not do every proton, right? It does not give all its protons away. It is just the first one. And it is not a strong acid, so it does not ionize, like every molecule is not ionized. You will find some phosphoric acid itself in the solution. So how does this proceed? What happens is the electron from the oxygen, the lone pair electron, it goes and attacks the hydrogen on the acid. And out of hydrogen and oxygen, oxygen is more electronegative, right? And therefore, it will try to keep the electrons which are between them, it will try to keep it more towards itself. So what that means is that this bond is going to break and the electrons are going to shift onto the oxygen. And we result in hydronium ion and the negative H2PO4. Now it is a good idea to, to draw these lone pairs of electrons. They help you see the mechanisms better. Okay. So now, as I told before, that phosphoric acid is not a strong acid, so I do not suspect the solution to be entirely made of these two things. So therefore, instead of using a forward arrow, I'm going to use an equilibrium arrow. That means they can go back, forward, right? Depending on the conditions. All right. Now, this was one of the terminology that we use. There is another terminology, which is the Lewis acid or a Lewis base. Now, for this thing, the condition is an electron pair. If something accepts the electron pair, it is an electron pair acceptor, we can term it as a Lewis acid. On the other hand, as you might suspect again, it is the opposite of of an acid. So a Lewis base is an electron pair donor. Okay, so in the Bronsted one, the condition was a proton. In the Lewis, the condition is an electron pair. So as an example, if you have a fluoride ion and you have BH3. You can call it borane. Now, boron, as you might suspect, actually not suspect, but you will find in my later videos that boron is very picky. It is not satisfied with anything. Right now, it has three bonds around it, right? So it has a total of 3 times 2, which is 6 electrons. It does not have an octet. So it is saying, I want an octet, right? Where are my other 2 electrons? So what it does, it accepts the electron pair from the fluoride ion. And this results in forming this. Now I'm not using the correct types of bonds here, okay, because it is a tetrahedral structure. So it should actually be drawn like this. Right, there are wedged bonds, there are dashed bonds, and 2 are in the plane of the page. Again, it is helpful to draw the lone pairs of electrons. And I drew the negative charge on boron. And how did I know that? You can do a formal charge calculation and you will see that the boron ends up having a negative charge. I will make a separate video just for that calculation because it is an important calculation. It helps in many reactions, right? Getting the correct charge on the molecule helps you see the reactions better, and helps prevent mistakes. So the boron has the negative charge here, and this is the reaction that you will get. Now here, if you are not familiar with this drawing, the dashed bond means it is coming into, oh, it is coming into the plane of page. And the wedged one means the bond is coming out of the plane of page. And the simple bond, a single line, means it is in the plane of page. So you can try to imagine what this molecule looks like. All right, so this was the basic definition of being a Lewis acid and a Lewis base. And first we did the Bronsted acid and a Bronsted base. Now there are molecules which can be classified as both a Lewis acid, Bronsted acid, or Lewis base, Bronsted base. But there are some molecules which can only be classified as one of the two. But generally, the thing is, generally, the molecules which can be classified as a Bronsted acid, Bronsted base are also Lewis acid, Lewis base. But molecules which are being classified as a Lewis acid, Lewis base may not necessarily be a Bronsted acid, Bronsted base. For example, if you look at this example itself, right? This one, they're not dealing with any protons. So how can you tell which is the Bronsted acid or which is the Bronsted base? But in the top reaction, if you look here, the oxygen in the water molecule gave away its electron pair to another molecule, right? So like it looks like it gave away the electron pair, and something which is an electron pair donor is a Lewis base. On the other hand, the oxygen, which is in the phosphoric acid, it took the electron pair which was in the bond between oxygen and hydrogen. So you can treat as an electron pair acceptor, and therefore you can say it is a Lewis acid. Right, so you can say a Bronsted acid, Bronsted base is a Lewis acid, Lewis base, but the other way around might not be the case. And then there is one concept which is sometimes misunderstood. It is that when you break a bond, it takes energy, right? And this is intuitive. You can see, okay, if I want to break something, I need to put in energy. But then if you make a bond, you actually release energy. All right. So when you break a bond, it takes energy. When you make a bond, it releases energy. So just keep that in mind when you look at reactions, because that can help you determine whether a reaction is endothermic or exothermic. Exothermic means it releases energy when it happens, and endothermic means it takes energy to go through the reaction. Now here, if you look at this reaction, what can you tell about the nature of reaction? Is it endothermic? Is it exothermic? What does it look like? If you look closely, the only thing you are doing in this reaction is making a bond, right? And if you are only making a bond, that means you are releasing energy, right? So it looks like this reaction would be exothermic. But then, on the other hand, in the top reaction, you have one bond which is in the process of making, and the other bond is in the process of breaking. So how do you know, like, whether it is endothermic or exothermic? Now, this is the part where you will have to look up the bond energies. You will have to see how much energy is in the bond of oxygen and hydrogen, and how much oxygen and hydrogen, like, it might seem that they have the same energies because they are the same atoms involved. But if you look at the other part of the molecule, right, such as this, it is not the same as this. So the energies would be different. And when you look at the table, you will see that. So this is the basic reaction of chemistry, the acid-base reaction. And it will help you in doing other reactions which are similar to these. And there are some combinations of reactions which incorporate this as one of the steps of the mechanisms. And I hope you enjoyed this video and have a good day. Thank you.